All right, we're starting an entirely new unit called Dynamical Systems. It's a lot of fun stuff. If you're a future teacher, future high school math teacher, keep in mind that a lot of this stuff has obvious applications to the real world, so your students might be interested in it. And it's fairly easy to do in Excel. There's no fancy algebra or anything, so you can use it as enrichment or as motivation for your students. Here's a quick preview of the applications we're going to see. Population growth, savings account growth, radioactive decay. You might have seen those in previous algebra classes, but we'll be starting with them because they're fairly simple, and a single dose of medicine turns out to be related. Then we'll do some slightly fancier applications, get even fancier with a biology-inspired application. Then we'll step back and try to look at the big picture, see what kind of patterns we're seeing. We'll take a look at some physics models. Now I like science, and pretty much all the previous models we'll be talking about are science, studying how things work right now. But I also like engineering, which is making things that we have work better. And every now and then it's good to throw an engineering example in there to help people have a sense of what they can do to make the world better. So one that we'll be looking at is using dynamical systems to help a premature baby stay warm in an incubator in the neonatal intensive care unit. Then we'll switch to multivariable models. A few of what we just talked about is multivariable already, but we have a different way of looking at some multivariable models. So it's a bunch of exciting stuff. So I've said we're talking about dynamical systems. What does dynamical mean? Something that changes in time. And think about everything we just said. Does it involve changes in time in a way that a lot of our kind of linear programming stuff didn't, or other optimization stuff didn't involve? We're only going to be thinking about time 1, time 2, time 3, without thinking about what happens in between the times. So we're using discrete time. A class like differential equations does continuous time, and also Calc 1, Calc 2. Our way is easier. It does have a relationship to calculus using what's called Euler's method for solving a differential equation. And there's better methods for solving differential equations, and I'll leave those to your differential equations class to talk about. Why do we not care about what happens in between time 1 and time 2? Well, first of all, let's start simple, right? If some things only happen once a month, like unemployment rates only get reported once every month, in some sense we might care about what happens in between, but we have absolutely no data about it, and so we just don't worry about it. Or if we know things happen in regular cycles, like once a week, we might just want to check on the system once a week and get to ignore all the day-to-day variations. But here we want to know what the cycle is, like 7 days, rather than have things that have a cycle length that changes from one cycle to the other. That makes life a lot more difficult. One thing we really have to do is say what our time steps are. Is it second by second, or minute by minute, or century by century? And we almost always want all the time steps in our model to be the same size. When we're doing things in a calculus point of view, sometimes it's okay to have the time steps change from row to row, and it's good to be able to account for that, but we're not going to be doing that too much right here. Sometimes people use t for time. We're going to use n for time, like n is 1 and 2 and 3. We're going to use a for the thing that we're tracking, like amount. We'll be usually graphing it on the y-axis, but not always. So it's good to keep track of what our axis labels are. So we'll have a sub n is the thing that we're keeping track of as n goes along in time. If you write an underscore, that means that the thing comes after it is a subscript. So if we're just typing things quickly, we'll often write a underscore n. Is a function? It actually is. You give it n and you get back a. So some people, especially Wolfram Alpha, write this as a of n in parentheses, which is also fine. Thinking of it as a function, though, is a little interesting. We're used to functions where you give it n and you can plug in n to a formula and you get the value of a back. And if I want a of time 100, I can just get a of time 100. I don't have to work up to it with a of time 99 and 98 and so forth. But a lot of the time here, that's called a direct formula. Here, we're going to be doing recursive formulas where I don't know a sub n until I know a sub n minus 1, or I don't know tomorrow's value until I know today's value. And we're going to be looking at the change from one time value to the next, which we'll call delta. This is an uppercase delta, and I've just gotten lazy and written it with a lowercase here, but really it should be uppercase. So the change from one time step to the next, we'll call delta a sub n. And so if I don't know a sub n yet, if I don't know a sub n plus 1 yet, but I know a sub n, I can just solve this formula for a sub n plus 1. It's a really simple algebra, right? Just add this to both sides and switch the order. And this is what we'll be using over and over again. It's nice to have a formula that's so consistent. Tomorrow is today plus whatever the change is between today and tomorrow. Okay, so usually we'll have some function of the current value that tells us how things are going to change, and we'll need to know where the whole system starts, the initial value. Every now and then we'll mix in the current value of n along with the current value of whatever amount I'm tracking. Alright, so let's start with a savings account. We'll pretend we'll just get 1% interest per year. We'll take time steps of a year. We'll start with $1,000 in the savings account, but not make any new deposits. It's just that whatever interest we earn, 1% of the current amount, will get deposited back into the savings account. So that's all we need to define our model. You can see I've sketched out how it's going to look in Excel here. So give it a second, take a sec to think about how you would actually set that up in Excel, and we'll stop the video and switch to Excel.